Can everyone hear me okay? Okay. So this is a talk about the process we've gone through to upstream SVE support into QEMU. So I'm going to do a quick introduction about who I am, talk a little bit about the QEMU project and its development process, and then I'm going to talk about the bits and pieces that we've done for the SVE work and how we've gone about getting them upstream. And at the end there's going to be a little demo. So first of all, introductions. My name's Alex Bennée. I'm on the virtualization team at Linaro. I mostly work on QEMU, although I occasionally do a bit of KVM stuff. My email's up there. You'll find me on the Linaro channels as AJB Linaro on IRC, and in the QEMU channel, for historical reasons, you'll find me as SD Squad. And the colleague that I've done this work with is Richard Henderson, who goes by the nickname RTH. So let's just have a quick overview of what QEMU is. So according to the website, QEMU is a generic and open source machine emulator and virtualizer. So what does this mean? And the two main modes people come across it. The first one is in when it's being used to do device emulation in a hardware virtualization context. So this is the thing most people will be familiar with when you're using KVM. It doesn't actually just work with KVM, it also works with HAX HVF and other virtualizers. But in this mode, QEMU is basically mostly concerned with device emulation. The other mode, which I'm going to concentrate on for this talk, is for full system emulation. So we support 21 guest architectures, and we can run any of those guest architectures on any of the supported host architectures for QEMU. And we do this by means of a just-in-time recompilation engine that recompiles guest instructions into host instructions. It says 20 architectures there. We've just recently added RISC-V, so that was the latest architecture added. QEMU is a relatively old project. It was founded in 2003 by Fabrice Ballard, who some people may have heard of. And ever since then, it's had year-on-year growth in its code base. It's hard to see. There's a couple of small lumps when contributions picked up. So probably the big one was when KVM support started to get added in around about 2008. And that's also when the QEMU project started to see its first big increase in contributors and maintainers. There was a switch to Git in 2009, but that preserved all the history. And then 2012 was the point at which QEMU KVM, which was a fork that was of QEMU that was initially developed when KVM was first developed, was finally fully merged into QEMU, and now is a deprecated project. Everyone can work with QEMU. The project is a relatively busy one. It processes around about 500 to 600 commits a month, go into the master repository. A typical release is around about 7,500 commits, and of those 7,500 commits, at least 6,500 of them will have reviews on them, and we aim to have more. I'll talk a little bit more about reviews later on.
How many lines removed?
I haven't got it on this slide. I do on some of the later patches, you'll see. So, a couple of basics for the development process. We host our source code in Git. There's a master repository that we host on our own server. We do have submodules, although the submodules are usually for ancillary bits of software, things like BIOSes and stuff like that, which are helpful for system emulation. The development model is very much around pull requests, so we have a single head maintainer, although the person that might be doing the merging can move around, and typically the maintainer responds to pull requests from sub-maintainers who are responsible for gathering the patches from the wider community. It's very much old school in most of the discussion for the project happens on mailing lists. So although there is a mirror of the QEMU project on GitHub, we don't process any pull requests through GitHub. Everything happens on the mailing list. And there's the main mailing list, QEMU Devel, but we also have a bunch of sub-mailing lists for people that are only interested in particular aspects. So for example, there's a QEMU ARM, there's QEMU security for security-related stuff. There's a QEMU trivial where trivial patches can be sent. Although typically most people will send their mails to the subsystem-specific list and CC the main development list. The other main place where discussion about the project occurs is on the IRC channel. So that's hash QEMU, and that's on the OFTC network. So that's, most people are familiar with Freenode. OFTC is the other big IRC network. We have a reasonable level of documentation for an open source project. You'll find useful information in the doc tree and the source tree, and we also have a wiki. The stuff in the docs tree is mostly text-based, but we are slowly moving to having more renderable text that we can put online. So this is a little diagram I drew last week to illustrate the typical development process flow. So yeah, over there the developer will develop and test his feature. Once the developer is happy that their feature is complete, they will post the series of patches to the mailing list and request that their code can get reviewed. Hey, excellent. Yeah, so they'll request a code review on the mailing list. The output from that code review will either be a bunch of review comments from developers telling what needs to be changed, or a bunch of review tags, which are standard developer certificate of origin tags that you'll see on the mailing list, like reviewed by, tested by, so and so at a mailing address. In either case, these need to be picked up by the original author, wrapped up into the patches for their next iteration. And then they'll go around again, post v2 to the list. Eventually, when the patch series is deemed to be ready, typically the maintainer for the affected subsystem will accept the patches and stick them into his own next branch. It's not unusual for a maintainer to take some patches from a patch series that are deemed to be ready and let the rest of the patches go around for another cycle. The maintainer adds their own signed off to the patches to say that they're happy with it, and when they've gathered enough patches in their branch, they will send a signed pull request via the mailing list, but to the head maintainer to say, I've got a bunch of patches ready to be merged. And the head maintainer basically spends all his time taking pull requests from maintainers, all the other maintainers. He'll do some final tests on them to make sure everything is working, merge them into the master repository that's hosted on the QEMU Git. We do a time-based release, so we do about 3 releases a year. So as we get close to release time, we'll start tagging release candidates, and eventually, after we've eliminated any bugs or blockers, there'll be a QEMU release that comes out at the end. This is a graph from last year's KVM forum that shows the contribution rate for maintainers and contributors. So contributors are people that just submit patches to the mailing list. Maintainers are people that are listed in the maintainers file as being responsible for a particular subsystem. So as you can see, for contributors, we had quite a lot of contributors in the 2.0 system, the 2.0 release. By the next release on, 140 of them are still actively submitting patches, and then it tails off as we go on. Maintainers, we do a better job. This column, ignore this column, this is mostly because maintainers often go into the maintainers file the first time misspelt and then have to be corrected afterwards, so it confuses the scripts. But maintainers tend to hang around for a lot longer. But the point of this slide is to point out it's in the interest of the maintainers to make sure code going into QEMU is of good quality, because they're going to be the people that are responsible for making sure that the code is kept working, whereas most contributors have long since gone. So broadly, the upstreaming criteria for QEMU No regressions. We don't like breaking existing functionality. So at the very least, when a patch series goes to the list, we expect it to compile. You'd be surprised how many times patches go onto the list and the first response you get from the reviewer says, well, I applied these patches, tried to compile and it didn't build. And that's usually a sign that you're not going to get any more review comments because the reviewer will have just given up and moved on to the next task. There are always more patches to be reviewed. We have a make check system, so that runs a basic set of unit tests on the code and a couple of system tests. And we expect developers, when they post a new feature, to say that they have tested that the new feature is working. Even better, if they can add tests to our check system to validate that feature and protect it against regressing in future.
Do they have to describe how they tested so you accept that the test they've done is correct, or they can just say, I've tested?
You can be as verbose as you like, but it depends on the feature itself. So if you're changing core functionality of QEMU that everyone uses, then we expect quite a degree of testing. We'll probably want to make sure that we've added unit tests into our make system. But the very nature of QEMU means quite a lot of stuff is I've enabled KVM on this random architecture that only I've got access to,
and it works.
And it worked for me. And if other people have access to it, then that's great. So we have to take some of that on trust from the developer. Obviously, if someone who's reviewing it manages to build it and replicate the test case and it falls over, that again is going to be another black mark against the series. Otherwise, acceptable code. We have a coding style. It's not overly pedantic, but we do like it to be followed. It helps if all the code in the code base reads the same. We expect signed off by tags to say that basically a signed off tag means that you are saying I am legally allowed to submit this code and I certify that there are no reasons why this code can't be included in the code base. This follows the same model that the Linux kernel does for its code sourcing. We like every patch to get reviewed. As I pointed out earlier, there is still a bit of a gap between the number of patches that are reviewed and the number that finally get merged in, but it's getting better all the time. So it should be the minimum to aim for to have at least one reviewed by tag on every patch. And importantly, we want the patch series to be bisectable. So there's no point introducing a patch that in a patch series having a patch that breaks a compile or regresses something halfway through and say, oh, it's fixed in a later patch, because that makes bug hunting really, really painful. So every single step in your series should pass all its checks, and then that way, when we're hunting for regressions later on, it's a lot easier to bisect. Right, so with that introduction to the development process, I'd like to talk a bit more about Scalable Vector Extensions. So this is a new SIMD instruction set that ARM have introduced. And it's something that they're aiming for everything from mobile to high-performance computing. So what makes it different from most SIMD implementations is the size of the vectors that it uses is entirely implementation defined. Okay, so a valid SVE architecture can implement vectors from 128 to 2048 bits. Now the important thing about the vector extensions is they've introduced a number of new instructions that allow you to write code that utilizes these vectors without actually knowing what the system implementation size is. So the idea being that you can write a piece of vectorized code that will run on a mobile phone that might have a relatively small vector length and take exactly that same binary and run it on your high-performance computing, and it will run faster because it will be doing more elements at a time, but the code doesn't need to be changed to do it. It supports multiple floating point precision, so both double and single precision, but also half precision as well. Basically, each time you drop down in precision, you can get twice as many operations done per instruction. So I'm not going to go into more details about the SVE itself, but there are a couple of links I put here which you'll be able to download when you get the slides. Did a nice intro blog post that describes the instruction set. I did a talk about SVE at San Francisco Connect last year, where I went through more detail about a typical SVE string copy implementation that demonstrates some of the features of the instruction set. And there was also a talk at FOSDEM this year talking about some of the challenges that having large vectors brings to virtualization. So just a quick review of how QEMU's TCG system emulation works. We start at a guest PC. We read in a set of guest instructions. For each instruction, we disassemble it and generate a bunch of these things called TCG ops. TCG ops can be thought of as a sort of intermediate representation. So much like what a compiler does when it's compiling source code, except the source code for TCG's case is assembler instructions. There is a simple optimization phase, and then we generate host code from those TCG operations. And we emit that into our translation buffer and then jump into it and start executing. So the first problem we ran into, or the first problem that was apparent when we started on the work with TCG is how we're going to deal with these large vector sizes. So the TCG only, at the time, only understood the concept of 32-bit and 64-bit register sizes. But vectors can be a lot larger, but also the lanes that you're operating on can be a lot smaller. This might be a bit clearer if I show you the vector layout. So here we've got a 128-bit, the typical 128-bit vector, which might be accessed as a single quad word, or 2 double operations, or 4 singles, or up to 16 byte operations at a time. And for the TCG, this introduces a bunch of cost for marshalling, because if you've only got a 32-bit or a 64-bit TCG type to represent things in, what you end up doing is reading a single element of the vector lane out into the TCG op, going and doing your operation, and then storing it back. So this imposes quite a high marshalling cost. So it means for every instruction you end up doing more and more TCG ops. The back end has no idea that you're actually doing a vectorized operation, so it has to do all this with scalar operations. Now you might argue that you could pick some of this, get some of this performance back up by optimizing and doing some analysis on your output stream, but a JIT imposes slightly different restrictions compared to a compiler. Because we're running dynamically and translating code on the fly, we can't really spend too long analysing the instructions that we've omitted to find optimizations like a compiler could. QEMU also uses things called helper functions. So helper functions are bits of C code that get called from our JITted code, and they're typically there for more complex instructions that would be fiddly to do in pure TCG ops. But of course, if you're going to call a helper function for every single lane in your vector, you've also imposed the cost of creating a C ABI frame and procedure call, prologue and epilogue as you jump in and out. And also the helpers are only working on one element at a time, so you don't get a chance to use vectorization in the helper. So I did a more detailed talk about this at KBM Forum, where I talked about the detail of the changes we made, so feel free to watch that presentation at your leisure. But as to the actual solution, we'd had some ideas about this. So the first step was to send a RFC patch series. So RFC stands for request for comment, and this is basically, I've had an idea, what do you think of this? Importantly, RFCs don't have to be a complete implementation. The idea of an RFC is to stimulate discussion and debate. So you're not looking to implement the complete patch series that solves the problem. You're looking to implement a few patches that says, this is the sort of direction I think you're going. Do you think this is going to work? Should I spend some more time on it? both me and Richard actually sent our RFC patches to the mailing list on the same day. As you can see, they're relatively small, only about 200 lines changed. Richard's was a little bigger. But from that was the start of the discussion of designing the architectural changes that we wanted to make to the TCG. And in the context of upstreaming things, the important thing to note is we did this very early on. This was in August last year. And soliciting early feedback from the community really pays dividends. It means you don't spend a lot of time doing work and then have to redo it once they come back with a bunch of comments. So the TCG vet work went through a number of iterations. Eventually by version 11 we had a version that we thought was complete and ready. This time we were up to 7,000 lines of code. Now although we wanted to implement this for supporting SVE, we hadn't implemented any SVE instructions at this point. But it's important not, the project doesn't really want to accept code that's of no particular use. There's no point merging code that is going to sit there uncompiled and untested. So we converted a number of the existing AR64 instructions to use the new TCG VEC API to demonstrate its use, and also made changes to the host code generators for both x86, which is the common case, and for an AR64 host. So now the backends, when they know they're dealing with a vector, can use vector instructions in their implementation at the back. Pull request went onto the list in February. It's not unusual for the first pull request to fail, although people are generally very diligent about testing their pull requests. Often they don't have access to every single piece of hardware that QEMU is supported on. So that's when the pre-merge tests that are run by the maintainer are very important to catch any last-minute problems. It was only a minor compilation problem caused on an esoteric architecture. So version 2 was posted, and this has been already merged into master. So this will be in the upcoming 2.12 release. You won't notice, as a user, you won't notice any new instructions. This is all purely internal core code. The next major bit of work we had to implement for SVE was half precision floating point. So this is part of the ARM v8.2 instruction spec. It's an optional feature for ARM v8.2, but it's a mandatory feature if you want to implement SVE. So half precision floating point introduces a new floating point format, which is 16 bits wide. So this has a 5-bit exponent and a 10-bit fraction. So obviously the numbers that it can represent are across a much smaller range than a single or double precision number. Basically, half precision exists to trade bandwidth for accuracy. It turns out, for a lot of cases, you don't need to be super accurate in the number you're calculating, but what would be useful is doing more of them. So the sort of typical use cases you see for that, some graphics calculations only need a couple of bits of precision, and the big one is machine learning can get away with a lot less resolution in its floating point. Now for QEMU's implementation, we do all this with soft float. So this required making changes to soft float. So let's first of all let's talk about why we do this with soft float. So soft float is a BSD licensed library developed by a guy called John R. Hauser. And the reason QEMU uses soft float is because there's can be quite a bit of variation and difference between how guest architectures and the host architecture you're running on deal with floating point numbers. So although most ISAs these days are IEEE 754 compliant, there's enough wiggle room in the spec that you get things like different behavior for NAND propagation, different default NANDs, and some architectures implement different exceptions. And you also get a couple of things like ARM extended, ARM alternative floating point format. So for floating point, half precision floating point numbers, ARM has a particular way of representing numbers to avoid using the exception bits and instead represent a slightly bigger number. Now, Berkeley Soft Float is currently at the 3C release, but QEMU uses the 2A release, and that's because when SoftFloat was first added, we had to make quite a lot of changes to the SoftFloat code base to support it for QEMU's use case. And also, the subsequent releases of the 2 series had a licensing compatibility, so we weren't able to use later versions of the 2 series. So the first thing this led to was, well, how are we going to implement all these half-precision operations? There didn't seem to be an obvious way of doing it. So there was a discussion on the mailing list. We were either faced with the choice of patching our existing code, which was doable, but it would be a fair chunk of work. We could look at using 3C, which actually had half-precision float already added to it. Or we also discussed some other options, like maybe it's time to move away from SoftFloat and use glibc's soft floating point implementation. The initial discussions didn't really come up with any clear answer. So as code speaks more than just words, first RFC went onto the list in July, where we basically just imported all of SoftFloat version 3 and made the changes we needed to use it, and started incrementally adding a couple of new FP16 instructions. Again, this wasn't a complete functional patch set. This was posted as an RFC to the list to go, well, this is one way we could go. Is it worth doing? Unfortunately, it involved quite a lot of duplication, and we still had to make all the changes to SoftFloat 3 to support QEMU's use case. When we were doing this, we started discussing whether or not there was going to be any chance that Upstream, so the Upstream project, the SoftFloat project, would take the patches to the SoftFloat library, or whether we were effectively committing to holding onto these patches forever and being yet another fork of SoftFloat. Now, the SoftFloat project is a bit of a it's hard to call it a project because it's basically a one-man operation. And I did contact the author and discuss the options of getting things merged upstream, and he was in principle up for it, but he said practically it will be an as and when process. So that's not really the sort of thing we were looking for. So the next RFC I posted, I started making a bunch of changes to our existing 2A implementation to start implementing half precision. That went onto the list in October, but it was readily apparent there was quite a lot of problems with it, because the general process for implementing half precision was to take float 32 add, copy and paste it, change all the magic numbers to deal with the float 16, and errors are likely to creep in. So this wasn't particularly acceptable either. We could see it would be a lot of effort. So in November we had a sprint in Cambridge. So Richard came across to Cambridge. We both sat down at the computer and thought, how can we do, if we're going to own the SoftFloat 2A code, can we do it better? So the result of that was a refactored SoftFloat that added a whole bunch of floating point, all the floating point operations, which we posted to the list in December. Now, because this was, by this point, we were getting ready for a proper submission, we didn't have any ARM FP16 in, so this was all just making sure that the existing floating point behaviour worked. One thing I will point out, though, that at the end of this, we inserted 3,000 lines of code, but we deleted 3,850 lines of code. So we deleted more code than we'd added, but increased the functionality of the library because we'd also added all the half-precision stuff. There are a couple of iterations after review. The fact that we changed 49 files was mainly just because a couple of headers got moved around. But again, we were ready to go at version 3, but there was one small problem. This is a benchmark called DBT bench. It's actually just a wraparound end bench, but we use it for QEMU because it's quite good at exercising the code generation library. And you can immediately see the problem. The original floating point implementations in purple, bigger numbers are better. Unfortunately, we managed to generate a lot of nice, cleaner, easier to follow code, but it was a lot slower. So we couldn't merge it in its current state. One of the reasons for this is, in an effort to make the code generic, so we only had common code for all of our adds and subtracts, we had tried quite hard to represent floating point numbers in this structure called float parts, which was able to represent floating point numbers of all sizes. So we do the operations on a 64-bit fraction and then make the appropriate rounding changes at the end. We thought we were being clever because this fits into 128 bits, and the idea being that with 128 bits and an intelligent enough compiler, this can all be passed around in a single register as you call all your various subfunctions. What we hadn't counted on was the fact that because it's packed in a structure, all the shuffling, anding and masking that the function headers need to do to get the values in and out of the structure adds quite a lot of cost. So this didn't actually turn out to be too big a problem to solve. I discovered my new favourite GCC attribute. So this is the flatten attribute. What flatten does is it says every function that that this function can see in scope that's included should be inlined. So all of our nice, helpful generic functions will get inlined in this particular implementation of the add function. And when you do all that inlining, the compiler's got all the information it needs to dead code eliminate stuff, and it certainly doesn't need to start shuffling values in and out of structures in and out. So the result of that was we got all our performance back. So again, this is the original soft float stuff and the state of soft float when we started the work. And you can see we've got roughly broad parity, a bit slower in some places, a bit faster in others. There are a number of other instructions that we needed to support for SVE that are prerequisite requirements. These weren't anywhere near as hard to do as all the half precision stuff, but they still needed to be done. So we've got rounding, double, multiply, add and subtract from 8.1 and from V8.3 complex number support. So both of these are mandatory for SVE, and they were eventually merged just earlier this last month. A couple of other bits we need to we did. One of the problems with writing decoders in QEMU is it's quite a error-prone process if you're doing it by hand, because you're typically reading an instruction manual, looking at the bit patterns for all the fields, extracting them, extracting the register numbers. And it's quite easy to get this wrong. Having been bitten by this a number of times, we thought, is there a smarter way we could do this? So we've now got a decoder script that has its own little register description, instruction description language that it can process. So the decoder script parses a file that describes your instruction set, that describes where the fields are, and it will generate all of the boilerplates that you need to extract all the values you need for the code generation. It doesn't do the code generation bit itself, but it does all the boilerplate that's easy to get wrong. So that's already merged into the upstream project. You'll see it in the scripts decode tree, I think. Other stuff, we've already added the support for the expanded register size that we need for SVE, and we've added access helpers, and we've added all the migration support. So I think the important thing to get from this is when you're working on a big project, it really helps if you can break up your work into small complete bits of work in themselves and get them merged upstream as fast as possible, because otherwise you end up maintaining a very, very, very large patch series which becomes hard to review. The final bit of plumbing we needed to add was Linux user support for the extended signal frames. So when you have a signal firing, the signal can provide a context that describes the processor context to user space. And this is important for us because it's the basis of how our RISU instruction testing tool works. So again, that has already gone in. So that leaves the SVE patches themselves. So currently these are sitting on the mailing list. Fairly large piece of work, 11,000 lines of code across 67 patches, but it does implement 99% of the Linux user support. The only feature that we don't support at the moment is the first fault register. And the reason we don't support this is because we don't actually have any way of testing it. When we looked around as we were testing all of our various test cases, we found no programs used it because GCC and LLVM don't emit any code that uses the first fault register, and glibc doesn't have any assembler functions for any of its string copies or mem copies that use the first fault register. So all SVE enabled code that you're likely to compile will run with this, but it's obviously something we need to look at fixing. So now, this is my time to call for review. This is now the time to review and test. There's a GitHub tree where you can pull the current state of the SVE work from, and please join in on the mailing list and review the patches. We expect a version 3 to come out within the next couple of weeks, and they should apply cleanly onto the current state of master. Right, now it's time for the demo. So there were two benchmark programs we looked at. So the Himano benchmark is a product of the Advanced Computing Center in Japan, in Riken, and it does a fluid analysis. And Lulesh was the other one we looked at, comes from Lawrence Livermore in the States. Both of these are designed as benchmark programs, but they're designed for high-performance computing benchmarks. The idea being is they simulate the sort of usage patterns that you get with high-performance computing. So they're good for benchmarking, but without having to run a full, a typical scientific application, which might need several months to run.
A bit more.
A bit more?
Yes, okay.
Right. Let me just log back into my machine. Right. So, to save a bit of time, what you can see here is I've already run the high mode benchmark on, but using a binary that was being compiled with v8.0 support. So this just uses the normal Neon instructions. So I'll just kick off the SVE one. So I'll just point out, it gives an mFlop score and gives us a relatively low number compared to a 200 megahertz Pentium. This is because we're using soft float. Okay, so QEMU is never going to be fast when you're dealing with floating point mass for the reasons I pointed out before. But certainly it's perfectly usable for testing that your code is functionally correct. That takes about
a minute.
Okay. So the V8 version takes about 54 seconds. If you look at the SVE version, it takes 38 seconds. Now that's quite interesting. You would think that SVE was harder to emulate than Neon, but actually we get a benefit here from the fact that we're emulating a full 2K width SVE register. So every time we call one of our helper functions, we're zipping around and doing a whole bunch of operations at a time. So we're saving on the marshalling cost compared to Neon. I can actually demonstrate this by looking at the...
Can you change the size dynamically?
Of what?
Of the vector.
Not in our current patch set, but it's something that we need to add. And maybe this is a bit clearer. I don't know if you can see can you see those numbers there? The red doesn't really come up very well. But so the top is the SVE version, and the bottom is the Neon version. And what you can see is in the SVE version, we spend much more of our time in our floating point emulation routines, which means we're spending less of the time doing the marshalling that we have to do for the neon stuff.
Can you invert colors?
Invert
colors?
Invert colors.
Oh, invert I can't remember off the top of my head.
Just select the mouse.
Oh, so here.
Base 38%, and the bottom one's 40%, right?
Yeah, but that 40% is not the Mullad.
It's
The Mullad is 24% here. Yeah, we're not quite sure where this one came from. I think it's a difference. Obviously, we've got slightly different instruction patterns, so this, it's doing more of this packing stuff.
Yeah. And it probably has tail loads and tail loops. Oh, they better.
Right. Anyway, enough of staring at the numbers. Is that enough of the perf dump? Right. So finally, I'll just talk about future work. So obviously, I mentioned first fault register before. So there's the first fault register and the ability to do non-fault loads. So this is a feature of SVE that allows you to handle the cases you get when you get to page boundaries. So in a typical system, if you have a mapped page and then the next page is unmapped, you'll get a fault if you run into that page. And you'll see this if you look at the string copy functions that are done in AVX or SSE. They spend an awful lot of their time checking the pointers for the source and destination strings aren't going to run off into the page next. Otherwise, they need to test whether or not that's going to fault before they run. With SVE, you just say, do a copy, and if it hits the page fault, don't worry about faulting, just set the first fault register, which can then be checked, and then you've worked out where your boundary condition is. System mode emulation is currently out of scope for the work that we've been doing. It was the main use case that people said they wanted from QEMU support was to be able to debug user space applications, and the Linux user support is certainly enough to do that. There'll be some more work to do system mode. It basically involves supporting the additional system registers and handling the ability to change the vector size between kernel and user space. And there might be some call to do some more performance work. So the TCG generator is fairly bare bones and simple, but one thing that we have noticed is we could be making better use of the host registers. So when vectors were initially introduced, the key to getting efficient use of vectors is to keep the value alive in registers for as long as possible and do a chain of operations to it. But QEMU has to make sure that it stores the results of each operation back into its register file. But what we could do is make sure that even though we've stored the value back into the register file, we reuse the value that's still in the register for the further follow-on calculations rather than keep loading them back and forth. The other option, the other thing we could look at for performance is whether or not there's any way we can make use of the host FPU instead of soft float. This was actually a thought I had when I posted the version 4 changes, because there was a fairly significant regression in our square root performance. And I posted an experimental hack that I spent about half a day on, and I wasn't intending to do any further work on it because I had other stuff to get done. But you know, it was yet again, here's a random idea I've had. What do people think? And Emilio Cotta at University of Columbia posted an RFC yesterday. So I just thought I'd show you the benchmarks that he posted with the set. So what he's done here is still in the helpers, so we're still going into the helpers, but he's actually set it up so you can use the hardware floating point to do a calculation. But if you hit any conditions where you're likely to get the number wrong, so if there's any nans or whatever involved, we then fall back to the soft float code. And his initial numbers are fairly impressive. So again, here's where we currently are with soft float. And we've got improvements of up to 2 and 3 times performance by using the host floating point. So this is going to be the patch that I'll be spending next week reviewing. So thank you for that. And with that, are there any questions anyone has?
What do you do about semantic differences between x86 FPU and ARM FPU? I mean, there's more than just the NANDs and the likes. There was also precision differences between the two.
Ah, right. Okay. Not so. Yeah, the precision differences you're talking about are between x87 and yeah. So Intel's SSE is 60. SSE is IEEE, so it does 64 and 32-bit. So as long as you're using SSE instructions, you're fine. You can't use the x87 because it works at a different precision. And in fact, I've found out to my cost x87 will also do things like silently drop NANDs and stuff if you put numbers in there. So yeah, basically you have to make sure there's no x87 code emitted by the compiler. Yep.
I thought in SVE programs you could also make programs that are vector length specific, so only work on a specific vector length. So that probably means that in QEMU, if you want to be able to emulate all possible SVE programs, you have to make vector length. You have to support all the vector lengths.
Well, okay, very quickly repeating, I think it's possible for SVE programs to be written in the style that it's vector length specific, will work correctly on some vector lengths, not correctly on other vector lengths. And so for that reason, I think if you want to support all SVE programs, you might have to support all possible vector lengths. I'm a bit hand waving here.
Yeah, well, so QEMU supports the full size, up to the full size vector length, so we have no problems there. I'm not entirely sure how you would write something.
So when I asked that question, the way that you would do this is right now with inline assembly by changing the system register that tells the size of.
Ah, right. Yeah. So now there is a system. So there is a system register that controls the size visible to EL0 and EL1. So the idea being that I'm not entirely sure what the use case for is the kernel would have access to the full size vector length, and then user space could have access to smaller size. But the program doesn't. The program doesn't know what the size is unless it's set that register. So you have to use some sort of hack to get that in. There is actually support in the kernel, so you can interrogate the kernel and say, what is my vector length? Or ask the kernel to set your vector length to be smaller. And currently we don't do that. But that's something that would be easily supported once we've done the system work.
Yeah, but the thing is, if you're trying to ask what is your vector length, then you shouldn't be doing SVE.
Yeah, it's definitely against the spirit of the programming model for SVE.
Exactly.
Right, any more questions?
Good job.
Okay, thank you very much.